last lecture. And we start speaking about non-Markovianity measures. So in the morning, I have introduced the idea behind memory effects in a quantum dynamics, which could be in a picture, can be described as follows. Here we take the time axis, and here we draw the trace distance depending on a particular choice of initial states, say rho 1 and rho 2, and we observe its behavior as a function of time. As we have said, given this is the initial value, if this quantity is monotonically decreasing, then we say that we have a Markovian process. If this quantity at some point in time rises again, then we speak about a non-Markovian process. And the idea behind this is the fact that this quantity, this trace distance, which is here plotted as a function of time, is a quantity which gives us information about the distinguishability of quantum states, given that we can perform a measurement on the state only, so that we have only access the system degrees of freedom. From this definition, one can also introduce say a more precise mathematical statement, which allows us also to introduce a quantifier of this memory effect. And the idea simply is, let us introduce the quantity sigma depending on the choice of initial state and as a function of time, which is simply the derivative with respect to time of this trace distance rho 1, 2, rho 2, having in mind that this time evolution is driven by a certain quantum dynamical method. Now, given this definition, one immediately sees that Markovianity is granted if for all couple of possible initial states and for all times this quantity is negative. While if at least at a given time, at least for a given pair of initial state, this quantity rises again, we can say that the process is non-Markovian. So we give the following definition: a quantum process, in the sense given in the previous lectures. So we call quantum process a collection of quantum dynamical maps, not necessarily depending only on the lapse time, such that each of these maps is completely positive trace preserving for all positive t. We say that the quantum process is non-Markovian, so we are providing a definition of what we mean by non-Markovian in this quantum setting, and I will try to later to come back to a classical notion. If there exists a pair of initial state, say rho 1, rho 2, rho 0, and if there exists a time t such that for the given pair at the given time, this quantity, that is to say the derivative of the trace distance, is strictly positive. Of course, here one could write if there exists at least a pair and at least a time such that. So in a sense, we use this revival of the trace distance as a signature of non-Markovian. Given this signature, in particular, we can easily find out that if we consider a quantum dynamical semigroup, as said before, or more generally, a collection of CPT maps which are divisible in the sense that I described in the previous lecture, so that I can split this time evolution into as many smaller pieces as I want, and this can be divisible either in the sense of CP or P maps, so that I can split these in single contribution which are added to CP. Then for these two kind of processes, for sure sigma is always either negative or equal to 0. So according to our definition, these processes these quantum processes are indeed Markovian, so they do not show up memory effect. Sorry? In principle, yes. So, given this definition, in a sense, it's easier to say whether a quantum process is non-Markovian than vice versa. Because unless, of course, if I have the analytical expression, if I know that the dynamics is driven by a quantum dynamical semigroup, then I know from that. But indeed, if I'm not aware of how the process works, so I'm only relying on an evaluation of trace distance, and evaluating the trace distance amount to being able to perform tomography at the system state, in principle at an arbitrary time. So in principle, I don't need any information about the mathematical structure of the quantum dynamical map or on the form of the differential equation or integral differential equation for the statistical operator leading to that time evolution. In principle, I only need to be able to perform experiments on the system, tomographic in the sense that I can reconstruct the schematics, the statistical operator, at arbitrary times. In this respect, if they don't have any other information, it's for sure easier to find out non-Markovianity because you need just one pair and just one time, provided you are able to. While for Markovianity, in principle, we should check that whatever the choice of initial pair, whatever the choice of time, the trace distance doesn't change if the time evolution is uniform, and all in that case. So it's always, yes, if it always equals. So what I have done up to now essentially is to define the breaking of monotonic loss of distinguishability as a signature, a criterion, a definition for non-Markovianity. I take it as a definition. Well, this depends. I mean, if you're only relying on experimental observation, in principle, yes. Though it is typically the case that no Markovian effects show up for short time. So it's in any case not a strong requirement. Because typically, if you have revivals of trace distance, so they are associated to phenomena which, with elapsing time, they die out. So on the other hand, if you have information of the dynamical map, then now, given this definition, I can also, the suggestion was also to provide a quantifier of non-Markovianity, so a measure. By considering the amount of these revivals. For me, it is important to distinguish between the definition, so the signature of non-Markovianity, and the quantifier. The key point is the signature. And for example, coming back to one of the questions of this morning, one could consider other quantities, such as relative entropy, which still behave in the same way under the action of CP maps or CPT maps, that is to say contraction, and to take them as signature of non-Markovianity. And in the end, this leads to similar results. Given this choice, then you can provide a quantifier. Of course, there are reasons in favor of the trace distance, but for the time being, it's fine like this. Now, let me simply introduce this measure associated to the process, so to the collection of time-dependent maps. And what is it? The idea is that I want to sum up the revivals, so I can formally write this as the integral over time of this sigma depending on ρ12 of 0 and time, and integrate when this quantity is positive. So this is the derivative, I integrate when it is positive. The idea is, however, that I have also to keep into account, it is also an important point, that this quantity depends on the choice of initial state. So I have to maximize over the possible choices of initial states. Because there might be pairs that do not show up in the memory, pairs who do. And then there are a wealth of results in this transaction, in this connection, pointing to the fact that indeed it's enough to consider the maximization procedure over states which are orthogonal and on the boundary on the space state. So there are other results going in that direction. This is, in a sense, the simplest statement. So other information you can find in the references I mentioned for these lectures, but this gives the main idea. And if you want, having in mind a simple situation in which this is the trace distance and there is only just one revival, this is time, say, the start of the revival, this is the end of the revival. I'm simply saying that one is evaluated the difference between the distance at time Pf, let me write it in a very compact way, minus the trace distance at Pi. So it's just the A. And if there are many revivals, I'm summing over here. This might be useful in order to compare different processes. Or for example, the behavior, just a second, the behavior of this measure with respect to certain parameters which enter in the definition of quantum dynamical math, such as strength of the interaction. Please. Yes. The idea is, okay, given that this is the definition, so when this derivative becomes positive, we have non-Markovianity, then how can we distinguish how non-Markovian a process is with respect to another? The idea is quantify this non-Markovianity. The Markovianity amounts to revival in the trace distance, so I am summing up all the revivals. Here I have taken the simple hypothesis in which there is only one revival. So a simple expression for this integral is simply the 8 of this point. And in doing this, you have to take into account that there might be pairs which do not exhibit revivals, and there are pairs which exhibit maximum revivals. Typically, what you should do is to start from states which are orthogonal. That is to say, at the initial time, the value of t is the maximum value, which is equal to 1. As I said before, this trace distance is equal to 1, takes the maximum value when they are orthogonal, maximally distinguishing. Okay, so these are the natural pairs which appear as optimal pairs for the evaluation. This said, I will try to also in answering a question which has been raised in the morning to connect this viewpoint to a classical viewpoint, at least to some extent, and point to the possible difficulties. So I stress once again, what we are doing is just looking at the statistical operator, which is all that we need in order to provide expectation value of observables. If you want quantities which depend on one single time, expectation value at a given time. We don't are taking care of information related, for example, to correlation functions. As I said, one has to distinguish from signatures, so the very definition, and then the way in which you quantify. You could use different quantifiers. For example, also a function of this quantity could be a sensible quantifier. You could divide by the overall amount, so you can normalize this quantity different ways. So in principle, there is a certain freedom. This is the choice that was made in the initial paper by Royal Line and Phyp, and it's a very sensible choice. But I mean, the exact value of this integral, whether the number is 1 or 10, that is not what matters. What matters is maybe whether this value grows as a function of parameters which specify the dynamics. So it's not just that the number in itself has a special meaning. So there are many points leading there. First fact is that you have a system interacting with an environment. And all the treatment that has been done before relied, for example, if you recall we said about quantum dynamics and semi-groups, on the fact that there was a clear separation of time scales between system and environment, which means that the environment is relaxing very quickly. This is a sensible hypothesis, provided, for example, the coupling is weak enough. But if this is no more true, then you cannot expect that, in a sense, the environment evolves by itself and only affects the system since it's much bigger, many more degrees of freedom. This is no more a sensible option. Or, for example, this might depend on the temperature, which still might be related. So at very low temperatures, you might expect that for certain systems, the back action of the system to the environment becomes important. Or you might consider system and environment which are comparable size to some extent, so that it's, once again, it would be an assumption which is definitely not natural to neglect the effect of the system on the environment. So strong coupling could be the guiding idea, not necessarily the only one, but the point is that in many realistic situations, you cannot assume that this semi-group law applies, because it relies essentially on this separation of time scales, typically with an idea with coupling or very brief correlation time in an environment, which are special situations. So you're looking for more general situations. And also the phenomenology tells you that the Limblad-Master equation is very good in many realms, typically quantum optics, where you have this very quick degrees of freedom related to the electromagnetic field with respect to the typical time scale, maybe for transition and so on. But in condensed matter or chemical, physical, these are the situations they call. This is seen from the viewpoint of more application and physics and so on. If you come more to a more formal mathematical viewpoint, for sure you are quite interested in asking the question, okay, now I've described what I mean by a stochastic dynamics in the quantum setting. Well, it would be natural to have stochastic dynamic featuring memory effect. How can I describe this? How can I? And this will be provide a description of a wider phenomenology, of course, on the side. I'm coming a bit to that right now. So, connection to classical viewpoint. Just also connecting to this question, on the classical side, we speak of a stochastic description. Means that there is something in the dynamics which is not under our control, even though we know that at the microscopic level the dynamics is deterministic. And this is typically described, so this kind of phenomenology is described, introduces a classical process. So classical stochastic processes arise, at least from the viewpoint of a physicist, to describe situations in which there is a randomicity that you cannot avoid and that you want to describe. Use classical stochastic processes for random dynamics. Let me use this vague term. Now consider a quantum setting, then in a sense the counterpart is an open quantum system description. Definitely, general, yes. So the idea would be that quantum mechanics is intrinsically probabilistic. And this from the very beginning, at this level. But on top of this, the interaction with other quantum degrees of freedom, which is not fully under your control, modified the dynamic of the system, and this you can think as an additional layer of stochasticity. And this calls, in a sense, for the introduction of quantum processes, let me use this vague word, for the reduced dynamics. And indeed, these quantum processes are, for example, the object that I've introduced as collection of quantum dynamic elements. So this is kind of the relationship. Now, in view of this fact, one might try to have a closer look to where the reason lies for the appearance of this trace distance approach. So this approach related to distinguishability. Yes. means that if you go for a stochastic description, your tools at the classical level is typically description in terms of classical stochastic process. The reduction of the dynamics brings with it stochasticity in the sense that with respect to the Schrödinger equation, which for example would preserve purity of the state, you take into account in an effective way of the interaction with the environment, which brings in dissipation, decoherence, the kind of effect I mentioned. So in this sense, it's the quantum counterpart of a classical description of stochasticity. So I'm making a broad connection, of course, but this is kind of the natural situation. And indeed, the whole framework of open quantum system description has arisen, coming back to the earlier, when one wanted to move the description of friction or of dissipative effects from the classical to the quantum realm. And there were problems in doing this, as you might know, and this has given rise to this formulation. So in the sense that here you have deterministic dynamic plus some randomicity, which comes from the outside world, from external potential, many classical degrees of freedom, which you cannot control fully. Here you have, in the very start, a probabilistic description, but on top of this, you have additional effects which are not fully under your control. There can be this kind of term of stochasticity induced. Behind this, for example, is the fact that you might know that one can use stochastic Schrödinger equation to describe noise effects in quantum systems, and then averaging the noise one comes back to statistical description. This is the frame. Now, given this framework, let me say a few words about what is a Markov process in the classical sense. We say that a stochastic process x t with t running over positive time is Markovian. And here we have a very well fixed definition, so something which is really helpful for developing theorem and so on. So a quite well-established notion of Markovian process. And saying it in a very rough way means that the probability that your process takes a value, say, x n plus 1 times t n plus 1, given that it has taken a previous value xn at the previous time tn, and the previous value x equal as xn minus 1 at time t n minus 1, till an initial kind of initial reference time, a value x1 at time t1. This is called a 1n conditional probability. So the probability to take this value given n previous values. Now, this object, if the process is Markovian, is only reminiscent of the last assumed value. This is the requirement. So x equal small xn plus 1 at time tn plus 1, simply condition on the value the previous time. And the point is that you do this requirement for all n in the natural numbers, and for all possible collection of times tn plus 1 greater or equal to 1. So the key point is that in order to say that the process is Markovian, you have to get access of every information over all n joint probability density. So a lot of information. But does this entail something simple at the level of the 1-point probability density? This is the idea. Because the statistical operator only gives the expectation values, which is, in a sense, the quantum counterpart of the 1-point probability density. So does this entail something at the level of the 1-point probability density? And the answer is yes. In order to be a bit more quick, let me write this whole object as n plus 1. This would be simply n, so that I write a little less, okay? So, given this condition, you can find out that the n-point probability density for a Markovian process, so the probability to take a given value at time t1, a given value at time t2, till time tn, is simply obtained by a conditioning of this form. So to obtain n given n minus 1 times obtaining n minus 1 given n minus 2, and so on till the last term, which is to obtain 2 given 1. So in a sense, once you know how to go from one point to the other, so the so-called transition probability, you are able to evaluate all possible joint probability distributions. So Markovian processes are simple because in the end you only need to know one object plus the initial condition, which is the value at time t0, which gives you then the value at time t1, which is p11, the value. So once you give the initial condition and the transition matrix, you have fixed the process. That's why Markovian processes are, in a sense, so simple to some extent and so widely used. Of course, you must admit that they provide a realistic situation of what is going on so that there are no memory effects. Now, let me prepare to go over to the quantum setting. As said, this is a transition matrix. Let me call lambda depending on Tn minus 1, Tn minus 2. So the idea is that this value x takes place in a finite set, so this becomes a matrix. In the dependence of a x n minus 1, x n minus 2, simply a matrix, a transition matrix. And this is my probability vector. So what we have is that Markov implies the following at a classical level. This transition matrix obeys the following composition law. So in order to go from S to T, you can make a stop at an intermediate time. And this is known as Chapman-Kolmogorov equation. This is a consequence of this Markov condition. So this is Chapman-Kolmogorov. But with the eyes of the previous lectures, this can be seen as a divisibility property. I'm saying that my collection of this object, this transition matrix, take a probability vector, transition matrix, and you go over to another probability vector. So it's the object, the stochastic matrices I mentioned in the morning. It's another name for the same object. So they send probability vectors to probability vectors. So they are the natural map which give the transformation in time of the state. And I'm saying that this transformation in time, can be split in as many pieces as I want, and each piece is a well-defined transformation. So this is a divisibility. Chapman-Kolmogorov can be restated as a divisibility property. As in exact analogy. Only now it's a composition law for matrices, which have to remain, each of these have to be a stochastic matrix. So in particular, we have the notion of positivity, only the notion of positivity, because in the classical set. So we could say that it is p-divisible. Another fact that you can check is that if you take two probability vectors, say p1 at time ts and p2 at time ts, these are probability vectors, you apply a stochastic matrix going from S to T, apply the very same one here going from S to T. So you transform your initial classical state at time S to the state at time T, and look at the distance among these two objects. Now, it turns out that also in this respect, now I will define in a second this distance, but it's the very same expression applied to the situation in which the statistical operators do commute, so that they are diagonalized the same distance. I'm going to write this in a minute. Now I simply write the fact that in this respect, stochastic matrices are still a contraction. So the distance, the initial distance between probability vectors, and this distance is defined as 1/2 the sum over I of the modulus of the So the idea is this is a vector. I take the I component minus the I component of the other vector. Component by component, take the difference and the modulus and sum over all this modulo. It is exactly what we did before. If you want, 1/2 the sum of the modulus of the eigenvalues. Only in the classical setting, you don't need to diagonalize. They're already diagonal. So it's the very same object. dk stands for, this is also known as Kolmogorov distance in the classical setting. So a Markovian process in the classical sense, which is the well-defined sense, if you want, has two special properties. On the one hand, Chapman-Kolmogorov says at the level of the map that the map is divisible. The transition map is divisible. At the level of the probability vectors, so it says that the action of the transition map is a contraction. Now, if these are consequences of Markovianity, if either of these properties is violated in the classical setting, it means that we can say that the classical process is no Markovian. Okay? Let me call this 1, this 2. Violation of either 1 or 2 is a sufficient but not necessary condition for detection of classical non-Markov. A sufficient condition. Why is it only a sufficient condition? Because as we said, in the classical setting, in order to define Markovianity, you have to take care of all n joint point probability lengths, so a lot of information. But here you have some kind of simple signature of non-Markovianity, which may unveil this non-Markovianity of the process. So now the idea is, so one idea to understand this approach is, as usual, we go from classical to quantum and say, now take the quantum analog, which we have already introduced, of 1 or 2, as quantum definition of non-Markovianity of a process. Why do we do this? So the idea is that we move from the classical to the quantum setting. But it's not so obvious how to do that, because let me make a slight, a simple table in moving from classical to quantum, which is somehow, to some extent, can be seen as one of the subjects I've addressed in this lecture. Please. Yes. And one can provide examples. So it's difficult to provide examples because typically you know a lot about Markovian processes in a classical setting. You know almost nothing about non-Markovian ones. But still one can point to examples, in a sense, in processes of the class that they exploited to produce memory kernel master equations. These are called semi-Markov processes. So you can also point to examples. You will also find reference in, not directly in that papers, but in papers quoted there. And so the answer is definitely yes. So this sufficient condition is not the end of the story, but still moving to the quantum setting where we think, but now I need to complete the table to answer you more probably. Please. Yes. The sign of stigma is directly related to this condition. It tells you that this, so if this is a stochastic matrix, it's a contraction. But if you consider the evolution from an intermediate time to a later time, if the map is not divisible, there might not exist a map driving you from the intermediate to the later time. And that's the reason why contractivity gets lost. Okay? I try to complete my picture and then we might come back to that. So the key point is that the very starting point in the classical setting was the endpoint probability distribution. Now I write it compactly, as I said. So the idea is for it to have the value xn at time tn and so on and so forth. Now I have to move the border a little bit. What is the quantum counterpart? We don't know. And it's not obvious how to answer, because in the quantum setting, to ascertain the value of a given variable means to perform a measurement. But it depends how to perform the measurement, and depending on how you have performed your measurement, this will influence the subsequent evolution. So this is a very non-trivial issue. That's why, in a sense, we have to content ourselves with objects for which the quantum counterpart is more naturally known. So transition matrices go over to these quantum dynamical maps. We have CP, we have other conditions, but still we know what is the natural quantum counterpart. Of course, also probability vector have a simple translation if you want. They go over to statistical operators. And then you have the divisibility in the sense of Chapman-Kolmogorov, which goes over to P or CP divisibility. So this condition have a natural quantum counterpart, and also the contractivity with respect to decay in the sense of distance among probability vectors. So this is 1/2 sum over I, the modulus of Pi minus Qi, goes over to the trace distance among statistical operators, which is 1/2 the trace norm between ρ1 and ρ2 of the difference between ρ1 and ρ2. So we are, in a sense, we have a way to connect the two realms, but we can do this at the level of 1 point probability density or at the level of transition matrices. We don't know how to do that at the level of n point probability density. And in a sense, one cannot expect that this can be done in a very straightforward way because of, this major obstacle, which is the fact that a measurement in the classical setting is not the same as a measurement in the quantum setting. So there are good reasons to think that one has big difficulties in trying to make so to say, a very close connection between classical processes and quantum processes. Now, as I said, this is only a viewpoint if you want to understand the result from the classical point, but I think it's quite interesting. And then I said, now we take the violation of this two condition 1 or 2, which is a sufficient condition in classical setting, we take as a definition in the quantum setting. One could take either 1 or 2. The trace distance approach is based on the condition 2. One could also rely on 1, as I have already shown there, and this was an approach which was proposed by Rivas, Welge, and Plenio. As I've already shown, there is obvious connection in the one direction. If divisible, then it is a contraction to the trace distance. One can work a bit further on this, and this is done in one of these papers, but for the time being, it's not. Like this, I just wanted to stress this idea of non-Markovianity related to revivals. Now, I go for an example and then try to dwell with initial correlations if time allows. So I go for an example of a system in which we can trace back non-Markovianity and relate it, for example, to coupling strength, so that also the physical intuition can be had. This is, in a sense, the workhorse in the field of non-Markovian dynamics, so the most simple but clear example that you can find in, for example, in one of those radios. example number 3 is temp James Cummings. Only a sketchy description as usual, but I hope this might allow. We have our usual two-level system, so to say, with its own frequency, omega 0, and is coupled once again to a bosonic environment characterized by a certain set of frequencies, but now we change the coupling. Coupling strength would still denote with G sub k, but this is no more a wiggy line, it's a straight lines which denotes the coupling, so that the system Hamiltonian can be written as omega 0 sigma plus sigma minus. This is just a projection onto the excited state. For the environment Hamiltonian, this is the collection of bosonic modes which I've already written in previous lectures. And now for the coupling, which is the interesting part, of course, we can write it as follows, as a sum over k of our coupling constant gk, an operator bk dagger, so creation operator on the side of the environment, and this sigma manus of the side of the system. Sigma manus applied to a vector pointing upwards, bring it down. So for the excited ground state, please. System omega 0 sigma plus sigma minus, which so in matrix representation, which would be the projection onto that. Okay, it's just because it's the blackboard is dirty. Okay. Sorry. So we have this contribution plus Hermitian conjugate. And this quantity, this operator as a whole, we might denote with B because it's then useful to put it into the formula as such. So this means that the interaction is such that if the system goes to the ground state, then the excitation is brought over to the environment and vice versa. So there is an exchange of excitation between system and environment. And the key point that allows us to provide an exact solution for this model, which once again we use in order to show the features of the rich dynamics, is the fact that the interaction Hamiltonian commutes with a full number of excitations. So in a sense, the number of excitation is conserved. We start with the environment in the vacuum state, which means that we have at most one excitation coming from the side of the system. So effectively, we are solving a problem in a two dimension, not in infinite dimension. That's why. And this goes back, this is well described also in the book by Professor Breuer. The first part, of course, then we go for the non-Markovian analysis, and goes back to a model by Wigel and Weisskopf. So that's the idea. Do you have questions? So you can believe me now if I say that given this conservation law, so the total amount of excitations, we are able to exactly solve the model. Since in the end we are restricted to a finite dimensional solution. So exactly solve the model means that we can also write down the exact expression of the reduced system operator at a later time t. And this is fixed once I say what happens to the population, which is multiplied by the modulo square of this function g, I'm going to do this in a minute, and what happens to the off-diagonal matrix element, which is multiplied by g of t. The rest follows because of trace conservation and emitters. Now, how is this G determined? G is determined by a two-point correlation functions of the environment. In particular, we can consider this correlation function of the environment, the expectation value with respect to the ground state, which is the initial state of the environment, of these operators B, now in interaction picture. So write them as B of t dagger. And this vector multiplied for convenience by I omega 0 t times, sorry, this is t1, t minus t1. This is our function f t minus t1. This is a 2-point correlation functions depending on these 2 times t and t1. Now, g is fixed by this function f according to the following equation. So you go through the calculation and find out that this 2-point correlation function fixes everything, in that it determines g according to this equation. The time derivative of g is equal to minus the convolution between f and g, together with the initial value for g is equal to 1. Of course, this equation might look now intransparent to you, but that is not important. Here, important is that the physics is driven by this 2-point correlation function, and this object fixes the dynamics. Okay, then you have to go through the calculation, otherwise you will never convince yourself. As a last point, let me express this correlation function, since it will depend, this B will depend once again on the coupling, possible value of the coupling, the sum over K, which are the modes. I combine all these in a spectral density. So if you go through this expression, you know that you recognize that you can write it as an integral of the spectral density as I defined it also in previous lectures. So this object is formally defined as J of omega is the sum over K, GK modulus square times delta omega K times a factor which has to be written as e to the minus omega 0 minus omega t minus t1. Essentially, it's the Fourier transform. This correlation function is the Fourier transform of the spectral density. So the idea is how to fix the model, choose a certain spectral density, which you suppose might well describe the environment. Then you will obtain the related correlation function, and this will determine the dynamics. What I will do now is to make a special choice for this correlation function, but the natural one, and for the related spectral density. The idea is now that the correlation function decays exponentially, which is one of the naturally expected behavior for a correlation function each time of the environment. So we assume that f of t takes the following form. It has a prefactor, gamma 0 lambda over 2. The idea is, I will come to that in a minute. The idea is lambda is related to the coupling strength, and this gamma 0 is kind of reference value for a Markovian dynamics that we will obtain. E to the minus lambda modulus of t. So, an exponential decay. And the Fourier transform of this object is a Lorentzian. So if this object, so the correlation, 2-point correlation function is roughly this expression. So it decays exponentially. Then J of omega is a Lorentzian centered around omega 0. Okay, the pictures look similar, but it's meant to be a Lorentzian anyhow. And the expression is something like lambda square divided by lambda square plus omega 0 minus omega to the power 2. So lambda determines the width at maximum on our Lorentzian. And here there's a factor, I guess, 2 pi or this for normalization. So this is the situation. Given this choice, we can work out the exact expression of G. And G turns out to take this value. It's e to the minus lambda t over 2 hyperbolic cosine of delta t over 2 plus lambda over delta hyperbolic sine of delta t over 2, where delta is the square root of lambda times lambda minus 2 gamma 0. So, and now I'm over with the auxiliary calculation. So if you want, but we need to have these quantities in front of the eyes, otherwise you cannot follow me. Now the point is, now we have the model, we have fixed the, in a sense, the correlation function on the environment. This lambda is a natural, 1 over lambda is a natural time scale for the environment. fine. So this expression tells us that we have a typical time scale for the environment. While one might see that gamma 0 can be taken as a typical time scale for the system. Because in the limit in which we will, okay, one should go through a more detailed analysis of the model, but you can to some extent believe me that when lambda is very big, so that its function is essentially delta correlated in time, I end up with a Markovian dynamics, which is ruled by gamma 0. So gamma 0 in a sense gives a reference, the inverse of gamma 0, a reference time, which is a typical time scale of the system undisturbed. Okay. So and this is where the physics come in. No? Now, the last step that we have to do now that we have everything under control is to write down the trace distance and its behavior in time. So we have to write the expression for sigma, which is the time derivative of our trace distance t as a function of time. Now, the expression goes as follows. We have a prefactor, which is the following form, 2 times the modulo square of g multiplied by delta p squared. Now I say what is delta p squared. The idea is that I take the difference of 2 statistical operators in 2 dimensions. Essentially, to fix them, I have to fix the difference in the population, which is the element 1, 1 for system 1 times the element 1, 1 for system 2. So I'm taking the difference of 2 objects of this kind. It's just enough to fix this one and the other one, and you determine the statistical operator. So I look at the difference between the population in the upper level for row 1 minus the one for row 2, the difference in the coherences for row 1 minus the one for row 2, and that's all. I fixed that. So that's why here I have a dependence on the difference in the population, and as you can imagine, the other dependence will be in the difference on the coherences. So the difference in the upper right matrix element. And this appears as follows. It's the modulo square of this quantity, which is in general complex, divided by the square root of g of t modulo square delta p squared plus modulo squared of delta c. This is in a sense it's not the relevant part because it has a definite sign. And we are looking for where there's a change in sign of the time derivative. So this is a prefactor. It's also important when we will look for maximization. But since it has a definite sign, it doesn't tell us anything about Markovian. The interesting part comes here. It is the time derivative of the modulus of g. This quantity can be either positive or negative and give us the information. So what happens? What happens is that if we plot g of t as a function of time, if we are in the situation in which the coupling is weak, and weak coupling means that this is a relationship among the time scale and implies that this quantity remains positive. Here you have hyperbolic functions, and as a result, if you look at the expression, it goes like this. While in the strong coupling, where gamma 0 is above lambda over 2, I use the same picture, what you have is that this quantity can becomes negative, so these become oscillating functions, and apart from details in the picture, something like this happens. So here you don't have revivals in weak coupling, while in strong coupling you do have. And this, if you look at this quantity, the ratio between gamma 0 and lambda, according to what we have introduced, is equal to the ratio between tau e and tau s. So that when the typical time scale of the environment is much smaller with respect to the time scale of the system, but in the weak coupling situation, you have a Markovian dynamics. when the time scale is comparable or becomes longer, then you go over to the non-Markovian situation. So in a sense, it's a natural description. I hope you could follow me here, and I go for the last part. Yes, please. Yes. Yes. Okay, maybe in the end, and commenting on the references, this will be the natural occasion to do that. Okay, now I made only a few names of two of them, but maybe in the end, commenting on the reference, this will be natural. So that I consider this as an extra time that that's okay. So detection of non-Markovianity and info flow. The idea is to connect to this notion of non-Markovianity. I give a motivation coming from the classical viewpoint, so to say. Now I go for something more physical to some extent related to information viewpoint. This is essentially the approach to Breuer-Line and Pilo, but I will come to that later on. So info flow, what we mean by this? Let me introduce these two quantities, a kind of internal information, if you want, which is this quantifier of the distinguishability of two given states, rho S1 and rho S2 of the system at a given time. Then let me speak about an external amount of information by considering the distance among a system environment state evolved from a certain state at time 0 up to time t, and the time evolved of another system environment state up to time t. What I mean? I take two different initial conditions, let them evolve, unitarily if you want, and consider the trace distance in this larger space, minus this contribution. So this is the overall information minus the, let me call, local internal information, and this I call, in a sense, external information. So this is the trace distance between rho S1 at time t and rho S2 at time t. Now, one can immediately check that this is a conserved quantity. So each of these is a positive quantity, they are both positive, and they are the sum of these two quantities, internal plus external, is a constant. Is a constant because if you sum them, you have the time evolution of this object, but the overall system being closed, the overall evolution is unitary, so the trace distance does not change. So this does not depend on time. In particular, it is equal to the internal information at time t0, and this is because in order to speak about the dynamics, we need the fact that rho S1, 2 at time 0 has to be of the factorized form. Otherwise, if they are not of the factorized form with the same factorized state, you are not describing the dynamics and you are not doing the same dynamics. So this quantity obeys this condition. Now, the idea is that since it is constant, if one quantity changes over time, the other also has to change. So the picture is the following. Here I have the system Here I have the environment. Here I take the time derivative of the internal information as a function of time. Again, it's the time derivative of the trace distance. So this internal information is my capability to distinguish the system relying on local information only. So performing measurement on the system. And if this decreases, so this is negative, means that information is, in a sense, is flowing out from system to environment. And this is a Markovian behavior. It might happen, and at initial time it must be like this, if there is a dynamics, because at least in the initial instant of time, the trace can only decrease. But at later times, it might happen that the time derivative of the same quantity becomes positive, so that there is a so-called backflow of information from the environment back to the system. So this is, you can call it this info flow from S to E, and this you can call info back flow from E to S. So the idea is that the Markovianity or non-Markovianity is called, defined through this trace distance, is called memory, because somehow to distinguish the systems at an intermediate times, in order to do that as good as you could do it at the beginning, before the dynamics started, you need to retrieve information which are now located in environment. So you, in principle, you should need to perform a measurement also involving degrees of freedom in the environment. And you speak about non-Markovianity when at some point in time there is a revival of this trace distance, which means that some information which is temporarily stored in the environment can come back. In a Markovian situation, information only flows from system to the environment, and in a sense gets lost there. So there is no back. You don't call it memory because it's not stored, it's lost. You call it memory if it is stored and can be retrieved. So this is a, sorry? Yes, because this is what I've now called is internal information, also according to the way of writing that we have used in the review, is just the trace distance in one. Here, internal is to stress the fact that it's based on local measurement. So in order to assess this, you have to perform local measurement in the sense of measurement on the system only. And one of the beauty of this approach is that in principle you only need to perform measurement on the system. So on local information gives you information about the overall dynamics. For example, in that case, suppose you know that dynamics is driven in such a way, looking at the system you can feature whether the coupling was strong or weak, and so you can recover information of the complex environment. Somehow one use the idea of quantum. Please. The upper bound, I'm coming to that. Okay, there's another. So given this statement, now let us go for a quantifier of the maximum revival. No, that was your question. And okay, all these things are related. Let me write down an inequality and we come back, okay? Now, the idea is that we have this balance. So if this quantity decreases, the other can increase. How much can it increase? That is one of the questions. So we can write the follow inequality. This external information as a function of time is bounded above by the trace distance between the time evolved of the first choice for initial state of system environment with respect to the product of its marginals. So this is the state at time t for system environment. These are the marginal with respect to, so you trace over the environmental degrees of freedom, so reduced state for the system, and this is the reduced state for the environment. Then you have a symmetric contribution in which you consider state 2 instead of state 1, plus another term, which is the distance between the state of the environment at time t, originating from the initial condition 1, and the state of the environment at time t, originating from the initial condition 2. And now I have to erase this, otherwise. So what is the statement? The amount of information which have been stored outside the system is bounded both by a quantity which expresses correlations between system and environment. So it means that you have stored in order to store information, this quantity has to be greater than 0. And in order to be greater than 0, it must be that at least one of these three is greater than 0. Which means that either there are correlations in the system environment state evolved from the condition 1, or the correlation in 1, or the states of the environment have been affected by an interaction with the system and in different ways according to the initial state. So these are correlation. This is effect of S on E. So the idea is that somehow one has a kind of understanding of where this non-Markovian comes from. It comes from the fact that during the dynamics, correlation has been established between system and environment, or the system has affected the environment, which is typically not the case if you think of a Markovian situation in which the environment is so big that it's actually not affected by the system. Now, exploiting this viewpoint, I can also say something about initial correlations. Then I'll make a kind of resume of the whole story. We are ready to say something about initial correlations, just exploiting this bound, and actually moving, in a sense, to a different framework. Because now, if I speak about initial correlations, you might immediately say, oh, but you just stressed at the very beginning that there must be no initial correlation in order to have a dynamics. Sure. And I will make this statement in a sense more precise, and then comment on the fact that, okay, then there is no well-defined dynamics at the level of the reduced system, but it might still be interesting from a physical viewpoint to detect afterwards these correlations, just performing measurement on the system. And this is what can be done in this approach. So I go for 4.2, initial correlation and reduced dynamics. The idea is, at least roughly, suppose at time t equals 0 we have a situation in which the initial state is the tensor product between rho s and rho e. Then we know that there exists a well-defined time evolution mapping. We know how it looks like. And the idea is that if this is the space of states of the system, so S of HS means the convex space state of the system. So the set where all statistical operators live. The idea is whatever initial condition I take here, there is a map phi of t which drives it to the corresponding final state at a given time. So there exists a quantum dynamical map. Okay? But this is for the factorized situation. Then suppose we have correlations. Can we say something? My initial statement was no. Now I make it a bit more precise. At least this is a very controversial issue. But suppose we have correlations, but of a special kind. And to denote this, I draw these arrows. That's my invention. The idea is that we consider zero quantum discord states, that is, states which are of the form, as I have written in my first lecture, a certain probability distribution, so numbers which sum up to 1, a specific set of one-dimensional projection on the side of the system, tensor product with a collection of environmental states on the side of the environment. Then what happens is that the dynamics, of course, given the fact that then you introduce an interaction between system and environment, so in the usual schema I introduced yesterday, the dynamics is actually well defined only on a subset of states within the whole set of states. And here I have in mind something like a Bloch sphere. No, sticking to C2, then you can fancy out really how the convex space of states look like. So it's a Bloch sphere. So if you take a state here, there is a well-defined CPT map which drives you to the final state. But if you consider states here, you still can introduce a map which, however, has not the physical meaning of the transformed state as a consequence of interaction with the given environment, with the given unitary. Then you have the situation in which the two states are entangled. For lack of better ideas, I denote it like this. So the statement is that rho s E is not of the form sum over E, certain weights, rho s E, tensor product rho E. So it's not a convex mixture of a factorized state. In this case, there is no way to define such a reduced dynamics, at least to my knowledge, but I'm afraid this will remain so. And all that you can do is go at the level of the overall Hilbert space, and that level, for sure, you can define a sensible assignment, which to an initial state for system and environment gives you a reduced state for the system. This for sure you can do because you consider overall evolution, take the partial trace in the end. But this is not a reduced dynamics because it cannot come from a map defined at the level of the system. So this said, which means that one can sensibly speak about what is the state of the system at a given time, both if there are no correlations, then I have a reduced dynamical map. If there are very special correlations, then I have a reduced dynamical map which works fine for a subset of states which is actually a commuting state, so a kind of classical domain. Or I have initial states which are truly entangled, but still it's sensible to ask the question, what is the state of the system? I can measure it. And it's then interesting maybe to infer from the behavior of this object whether there were correlation at the initial time. So in this sense, it's still a sensible question. And let me say just a couple of words about this possible assignment, just to point to the fact that it can make sense. How to make sense out of this? For a case of factorized state, we explicitly exhibit this dynamical map by going over to the Krauss representation. Now, what would happen like this? What is the natural candidate for this object? This natural candidate would be consider rho s at time 0, which is of this form. So let me replace it exactly with that form. Sum over I, some weights pi, the one-dimensional projector is fixed, tensor rho ei. Consider a unitary evolution ut. This is an operator on both system and environment, and take the partial trace. This is what you have to do. This gives you, in any case, the final state of the system. Now, the point is whether this can be expressed as a map acting on rho s at time t0 on. And one can immediately see that this can be done introducing a sum over I, sum over alpha beta of certain Krauss operators, which I can write as follows. I introduce certain k alpha beta of t, the very same which I used yesterday, which now will depend, however, also on the label I, and then this one-dimensional projector as I. Here I put rho s 0, and I consider the adjoint of this operator. So here I'm writing down an explicit Krauss representation for the map, so that I'm showing that it's a linear map, trace preserving, positive, and in particular completely positive. Still allowing for spatial correlations. I have to specify what is chi alpha beta ER, but they are essentially the same object I've considered the other day. Only the fact is now I have a collection of environmental operators depending on I, so the spectral representation of the environmental operator will depend on I. In a sense, the very same expression I introduced yesterday, only with this further dependence on the label I. So there's a collection of these objects. And in general, also the eigenvalues lambda will depend on this inside. So in this sense, I pointed to the fact that, also answering questions which were raised yesterday, it is formally possible to consider a well-defined map even in the presence of spatial kind of correlations. Only a stress that it only of reduced validity. And now I go for the very last part, which is about witness of correlations. And the idea goes as follows. I've already shown that the sum of internal and external information is a constant. Okay? In particular, is equal to the value of the internal information at time t equals 0. So there is kind of conservation of this quantity. So the two, if the one grows, the other decreases, and vice versa, and that was the initial point. Now, if this is so, one can also consider another point in time, say S, and rewrite the sum of the same object. Then you can rearrange term and exploit the fact that each of these contributions is positive, so that I come to the following inequality. If you compare the internal information at time t with the internal information at another time s, this is bounded above by the external information at time s. Because here you would simply add minus the information at time t, which is a positive quantity, you raise it. Now in particular, take s equals 0. So that this 0 means the initial state for the dynamics. So what we have here at the left-hand side, we have the growth of trace distance with respect to the initial value. So this quantity is bigger than 0 only if this is the trace distance at time 0, is equal to 0 only if at some point it goes above the initial value. But this is allowed if this quantity is positive. And when can this quantity be positive? Well, this quantity is the one that I've written before for generic time t. Now I rewrite it for time t equals 0. This is positive is either there are correlation in the initial state 1 on the side of a system environment, or the same quantity for one exchange with 2. So, or either there are correlation in the one of the chosen initial system environment state, or in the other, or the other possibility is that I have I have started my my experiment with two different environments. And in that case, there is no more an initial map. Now, if you consider a situation in which you take an arbitrary rho SE1 and rho SE2, so another initial state which is of factorized form, given by an arbitrary state on the side of the system, but the very same state that one would get from this on the side of the environment. So in that situation, these two are equal, so that is equal to 0. The second state is not correlated because it's in tensor product form. So your bound amounts to the fact the revival of the trace distance is just due to the fact that you had correlations in the initial state of the system. So in this yellow case, indeed, this might happen. And the age of this revival is bounded by the right-hand side, in this case. So this viewpoint can also be used in order to assess the existence of correlations in the initial state between system and environment, performing measurements on the system. So that's the beauty of the idea. And now I come for my last example, so kind of last tutorial, briefly, but I think I will manage. And for one time, we leave our bosonic modes. This is an example for is a spin star model. The idea is that you have a kind of central spin, which I denote like this, coupled to a collection of other spins, which I denote. So this is different from the other, so it's a square. These are circles all around, and they are coupled according to certain coupling constants, which still retain the name G sub k, and each of the spin has its own frequency omega k, while omega 0 is the reference value for our definitions. So the system Hamiltonian still is 1/2 omega 0 sigma z. As far as the environment is concerned, we have simply a sum of very same contributions, so sum over k omega k sigma z k. This is the spin operator for the kth spin around the central one. And then I write an interaction term of the following form, as usual, a sum over k, gk, sigma z, tensor sigma z k. So in the end, I will only affect, once again, the coordinates. Now, one can solve for this model since the interaction is relatively simple. And again, I will, in a sense, write down the solution pointing to what might be the interest. The interest will be that in this situation, we can in principle write down exactly what is the state of system and environment, and then have a look at this inequality and see that it is actually saturated for certain times, for certain value of time. Which means that if it is saturated, means that indeed it's quite profound. So that's so to say the goal of this brief exercise. So the idea is that I take rest of 0 an arbitrary initial state on the side of the central spin, while on the side of the environment, I take what is formally can be considered the infinite temperature state. So it's simply the identity normalized according to the dimension of the number of spin, which I can simply go from 1 to capital N. So the state of the system is fully so the most simple situation, so gives equal probability to all states in a one-finger space. And for this setting, I can come to the expression of the time evolved state. The point is that I need the time evolved of S and the time evolved of E in order to check the value of the different terms appearing in that bound. That is the key point. So I need to exhibit actually the state of the coupled system and environment. And it takes the following form. Is a sum over this MK. This MK denote for the different K spins whether they are in the state 0 or 1. So this is a collection of 0, 1, essentially fixing the different possible configuration of a spin. Then a weight which in principle might depend from this configuration, but the factors in this situation is equal to 1 over e to the n, since we have a uniform distribution on the side of the environment. And the action on the system is due to a certain unitary, and it's a joint to the left. This is a unitary acting on the system only, tensor product with the state of the environment characterized by a certain collection of numbers. It tells you this is a state, I don't know, +1, -1, according to a chain of values. These unitaries are actually quite simple. 1, 0, 0, and the other element of diagonal is E to the 2i sum over k, gk, our coupling constant, mk, which fixes the state of the cycle environment, times t. So a phase, essentially a phase determined from the state. So what you see is that you obtain a special class of states for system environment. They are indeed correlated because we have dependence on this label here and there, but in a sense you can write them as classically correlated. So it's a special kind of correlation. Now, given this expression, you can obtain, by taking the partial trace with respect to the system, you can obtain the state of the environment at time t, but this is simply unchanged. So this is equal to the state of the environment at time t0. Because if you trace out this part, you have just sum 1 over 2n of the all possible. This is a complete system, so just an orthogonal resolution of the identity. So the environment is left unchanged. This also answers one question which was raised yesterday. What happened to system environment? Does they remain factorized? No, they don't remain factorized. The environment might be affected, but might not. For example, in this random unitary description, it is not. Then one can also write down the expression for this rho s of t. I do it here. And then we come back to our bound. I have 1 minute left. Maybe I take 2 minutes, but no more. Okay. So rho s of t. As I said, the only relevant point is populations are not affected. The coherences are multiplied by a function f of t, and this function f of t is just the phase that I've written before. So this f of t is e times 2i, this sum over k, jk, mk, times. Sorry, the mk here. No, yes. Anyhow, the important point is that it is a phase determined from the coupling constant. Now, what happens? What happens is that now we are able to evaluate all contributions appearing here. So in particular, considering an initial state which is of the following form. So on the side of the environment, we have already said what is the initial state, is the identity. On the side of the system, we take a coherent superposition of states, let's say 1 and 0, meaning the two possible states for our spin, and we go through the calculations. So what we find out is the following inequality. have a contribution which is the distance between the joint state of system and environment time t. Instead of 1 or 2, I write plus or minus since they refer to these spatial states that I consider. So this distance from this object and the corresponding marginals. And on the side of the environment, we know that the state does not change. So we have this contribution minus the contribution due to the local change. And this is what is to the left of my bound, no? External minus internal. Minus or equal, and then I have three contributions, but actually one contribution is the distance between the environmental state 1 and environmental state 2 at time t, but they are unchanged and always the same, so it disappears. And the other two contributions are equal, turn out to be equal, so I have 2 times the distance between rho SE plus or the minus, it doesn't make any difference because they are the same quantity, with respect to its marginals. And now one is able to evaluate these quantities. This is simply equal to 1. This is simply equal to the modulus of f of t. So you have 1 minus the modulus of f of t, and the modulus of f of t has to be less than 1. So this is already the modulus of the difference of the quantities. And this is then turns out to be simply the triangular inequality, because to the right-hand side, we have the sum over these possible configurational values of 1 over 2 to the n modulus e minus y sum over jk and kt minus f of t. So the inequality holds, and essentially it boils down to the triangular inequality, because this quantity has modulo 1, and in particular it is tight when this quantity f of t is equal to 0, which happens, of course, at the initial time, but then in general also at later times depending. So here you see an example, and of course you need a simple example, because imagine you have to work out the evoluted state on the side of system and environment, then take the partial trace and so on and so forth, be able to calculate the trace norm, so it is in general a complicated task. So, however, given this simple example, you can really have a simple look at this inequality and see that indeed they are tight. Okay, so sorry for keeping you 1.5 minutes more, and I am over. Thank you very much. Now maybe I come to a kind of history, so to say. So of course the issue of Markovianity, of non-Markovianity, of a quantum dynamics is a very old issue, because Lindblad himself, right after writing this most famous paper in '76, in which derived the general expression of the generator of the quantum dynamical semigroup, I guess either in the same year or 2-3 years after, published a paper about the definition of quantum Markovian process. So the very definition of a quantum process, whether it's Markovian or not, it's an old history. And there was a lot of work, but it looks like in the recent years there was a kind of breakthrough, and this breakthrough amounted to the fact that one focused on quantities which are much easier to be handled with. So the original standpoint was, we have n-point probability density, somehow give meaning to these objects for all n and so on. This is a huge task, and it is not obvious that it can bring somewhere. Then more recently, and I would mention in this connection these two papers. So the one is by Breuer, Line, and Pilo. This is the paper in which this definition of non-Markovianity related to the trace distance and the definition of measure as I've given it, so a sum of revival, was first introduced. So this paper in 2009, I would say the seminal paper about it. And there, the attention was drawn to the fact that indeed focusing on the dynamics of the statistical operators only, so something that you can measure in principle, you don't even need to know the form of the map. Now in my presentation, I always came from that side. On the one hand, because I'm a theoretician, on the other hand, because it's a way to understand things, but in principle, you just need, in a lab, to measure, to perform tomography on the state of the system, provided you know that there exists the dynamics. But if the dynamics does not exist, means that maybe there are initial correlations, and these you can also detect according to this approach. Then there was this other important paper by Rivas, Welge, and Plenio, which I already mentioned yesterday, in which they introduced the idea that non-Markovianity could be associated to the visibility of the time evolution map in terms of completely positive pieces. So these were, in a sense, the two seminal ideas. Then there were many other contributions pointing to different quantifiers, for example, relative entropy or direct quantities. Then maybe even fix the quantifier, look for, even fix the definition, look for different quantifiers with respect to that measure. Also, in connection to CP divisibility, there was a proposal for a quantifier, which kind of the amount of violation of CP, and you consider that quantity, the logarithm of that quantity normalized over the overall violation of CP. So there are various approaches. Also, there have been a huge amount of proposal focusing on quantity, which in the essence depend on the complete positivity of the transformation. So quantities which in a sense are monotonic with respect with CP transformation. So any kind of oscillation, let me allow this word, could be in a sense somehow related to the idea of non-Markovianity following this approach. And related to this work, always Breuer, Line, and Pilo came to the idea to exploit some of these inequalities to use the revival of the trace distance as an indicator of the presence of initial correlations. And these two papers. This is a review on reports on progress in physics by Rivas, Welge, and Plenio, which appeared in 2014, which contains a lot of information and also huge literature. This is slightly more recent work, review of modern physics, by Breuer, Line, Pilo, and myself, which is also kind of putting ideas together, more focused on the trace distance, and where a major importance is given to this idea of information flow, which, however, let me stress, the idea of information flow was already presented in the seminal paper by Breuer. So the idea of distinguishability, trace distance, information flow appeared together in that approach. In this paper, there is also some information about the connectionship, possible connectionship between classical and quantum viewpoint, which was also addressed previously in a paper in the New Journal of Physics by myself, Breuer, and Smirne, which was work with me, Milan, on the subject line. But these papers are quoted here. So I just mentioned the, so to say, the seminal one and two possible radius. That is the idea. These last two are more specific on memory kernel master equation. This is a joint work by Heinz-Peter Breuer and myself, which appeared in 2008, which first made a connection to these semi-Markov classical processes. And this is another paper by myself, which is going to appear now on PRL, which is quite an extension of that approach. In a sense, it's closer to what I've presented. So these are more focused on this memory kernel stuff, which is not, in a sense, related but independent from the idea of non-Markovianity, because these are classes of possible dynamics. Then we still have to see whether they are Markovian or not according to this criteria. And this further reference is in view of there's been many questions about this example on collisional decoherence, random momentum transfer, and this is, at least in a certain spirit, is treated in detail in this physics reports contribution by myself and Klaus Hornberger. By the way, Professor Hornberger is also going to give a talk in, no. Okay, sorry, it's a pity. Anyhow, by myself and Klaus Hornberger, which was in a sense the theoretician involved in these some of the experiments about collision decoherence and so on. I'm all involved in some theoretical developments. It was involved in important part in the theoretical development and also in interacting with it. So I hope this gives an idea. Of course, by now there's a huge literature. Yes. For sure, and maybe I add a few more.
Yeah.
So, okay.
So along with your abstract, which you have sent, the bottom of it.
Okay. Perfect. Yes. So I will, maybe I will add a few more, making a very short, short comment so that one can understand what refers. Yes, for sure. Okay, and maybe if you allow me, a last thank goes to my institution, University of Milan, and also to Istituto Nazionale di Fisica Nucleare, which actually has supported my travel and in general my research. And thank you very much for your kind invitation.